The last major topic of the operating system course is on file systems. Effectively, what's a file system and how do you implement files and other things that live under a file system. So we have learned what a disk is. A disk is essentially, it appears as a linear sequence of fixed size blocks, and it supports the reading and writing of these blocks. Now there's a big difference between basically this view and what we see as a file system. What's a file and what's a directory? What does it mean to format a disk? Okay, so from the user's application view, we need to view the disk in terms of directories and files. And so the question is, how do you implement a file? What does it take? Is it just the data? Where do you store the name of a file? Or like the permissions of a file where is it? How do you implement a directory? And how do you find information for things? How do you ensure that one user can access only its own files but not another's data? Okay, and how do you know which blocks are free and which blocks are being in use? So essentially, a file system, it's a data structure that's designed for disks or for secondary storages, and it keeps the allocation information in the same storage as well as extra information about files like the name of the file, the last modification date, the size, permission, etc. And like there's also security access rights and timestamps, etc. Okay, more this whatever data structure that we design, it should support storage for a large amount of data. We are talking about terabytes, petabytes of data, and that this data would persist after the termination of the process, and we should be able to access it concurrently, meaning that multiple processes may be accessing the very same file system, and we have to make sure that the integrity of the data is maintained, yet the access should be fast. So file system essentially provides an abstraction for our processes. It provides an abstraction over this block-based raw data, okay? And a file system is essentially built around the concept of a file. This is where we store, this is the basic unit where we store data, and the concept of a directory. And as a matter of fact, what we mean as a directory is actually a specific type of file, so it's very related. And the file system should mask the details of low-level sector-based I/O operations, meaning that when you open a file and you read from a file, from the application point of view, all we have is the path of that, and we don't care about which disk it is stored on, or what the file system that it is doing. So when we look at the actual I/O, it's fragmented and distributed blocks on different areas of the storage, yet the operating system should mask all these details, and more, it should cache the recently accessed data in the memory. So we can see the file system abstraction levels in roughly three categories: the user level, the kernel level, and the hardware. In the user level, here we have our user process, and the way we access files is typically through library calls like fopen, fseek, and fread. And in the library, these library calls are then mapped onto system calls such as open, lseek, and read. And in the kernel level, these system calls access kernel file structures like as file, an inode, or vnode, and because like it's if you remember, these would make up some of the operating system resources that the kernel stores on behalf of the process. And within these structures, like then we have this virtual file system or VFS layer, which basically it takes the file, its path, and etc., and then it would map this to file system specific calls, meaning that when you do an open here, and if the file resides on a fat file system, then you have to execute a different specific call. If it exists on an X3, then it will be different. If it exists on NTFS, then it will be different, right? So the virtual file system would then convert them to file system specific calls, like if it's a fat system, it's like fat lookup, fat open, fat read, and etc. And at the lower level, then these calls should be translated into device driver calls, okay, as such, which will then be executed at the low-level I/O instructions, for example, the SCSI protocol. So what do we expect from our file system to support operations? Of course, we need to write and read, often via a position pointer that keeps track of our position. This is stored in the by the kernel, in the kernel space. Seek, which is the adjusting of position pointer. Truncate, which is trim some of the data from the end of the file, and the common case is the all data, meaning that you truncate the data to size 0, you clean up, and then append right at the end of the file. And at the level of the directory, then we need to it should support create, which is locate space and enter into a directory, create a file. And deletion, basically removing from directory and releasing the space that it used on the disk. Rename, which is changing the name of the file inside the directory, or move a file between two directories. And more, we should support the changing of attributes, such as the changing of the owner, permissions, the type, the timestamps, and also some extra operations like locking a file or regions or map them to memory. Now, what do we need? What are the design issues and constraints towards implementing a file system? The design issues is, how do we map the file data to blocks on the disk? So that is an issue. How do we represent, where do we store the attributes or the metadata data representation? And what we mean by this is, to think of the name of the file. Where you store the name of the file, it's not in the data of the file. It has to be stored somewhere else, or the permissions, or the size, the last access time information. All these things are basically needs to be stored. How do we organize a directory? What kind of data structure are we talking about? How do we keep track of the free blocks on the disk? And while we do them, then we have to operate under the constraints that that are imposed by the storage media that we have. So obviously, whether it's read-only or writable only by once, or its block size and so on. And we have to think about the size constraints, meaning that how much is the disk that we want to support. For example, if it's a floppy disk, it can be as small as a 1.4 megabyte versus it can be a petabyte disk or tape. And the storage organization, is it single disk that we're talking about, multiple disks, or cluster of disks, or network access storage? These are all constraints that are important for file system design. And a file system should also support the integrity of the data, meaning that since it's a data structure that is stored on the disk, we have to ensure that after a reboot or power off, the data that we store is maintains its integrity. And as we access files and directories, we have to implement them efficiently so that it minimizes any overhead and delays. And it should minimize fragmentation, maximize the size for files on a disk, and it should support recovery and repair facilities in case of a system crash. And the storage should be able to dynamically grow, shrink, or change. It should support snapshots and versioning, such as the macOS Time Machine, or like a Solaris ZFS, where we should have some support to roll back to a past state of the disk, accounting and quota support, index and search, encryption of the data on the disk, or automatic information of infrequently used files. So these are all things that modern file systems support. We will not be going, we will be touching some of these issues, but keep in mind that these are all things that are important for a file system. So we start from a file concept. From the user point of view, a file is the only unit, it's the essential unit through which a data can be written on storage devices. So we write data in terms of files. It's a logical storage unit or abstraction. You hide the details of storage devices. Okay, you don't care about the sectors and other things. You hide details of allocation, which blocks are stored, which blocks are being used to store the data or the file. And we need to store the information, like not only the data. So when we talk about a file basically contains, like we have the data, okay, but then there's also the attributes, okay, and attributes means, for example, the name, okay, permissions, last access, size, etc., etc. And so we should also be storing all these basically attributes of the file, and whether it's represent data, whether it's an executable, and so on. And note that when you create a file, its lifetime is actually, and it becomes independent of the process, the user, or even the system that creates it. Meaning that, when you have a file that's stored on some storage device, years later you should be able to access it. Okay, of course you should have like a computer that can read it mechanically and supports this file system, but it becomes independent when you create a file. Now it has a lifetime of its own and it can move on. So the first thing that we will discuss is file block management, meaning that when we say here, it's basically, remember that in the case of a file we need to store the data, okay, and this data basically, you can imagine that we have blocks on the disk, okay, so it probably spans multiple blocks, and what we assume is, if I have a data, logically it's a continuous storage reason, meaning that I have like the data, the first say 4 kilobytes is here, this second one, and so on. So if I have a 16 kilobyte data, then I should have this consequent to it's a logically continuous storage that I have here. But actually what we have is we have actual data blocks which may or may not be distributed in different regions of the disk, and they can grow. So we can add one more, or you can delete, can shrink, or maybe we delete them all. Okay, so they should be supported. And more, these file blocks, when we are accessing them, we may be accessing them sequentially, meaning that if I have this and if I'm reading them, maybe I'm accessing them in this order, okay, or I may be accessing at random, okay, like a random access memory, okay, which is the case for index files when we have, for example, a database. So when the question is, if I want to like store the data of a file in multiple blocks, then how do I allocate the blocks on the disk? And note that spatial locality of files, okay, meaning that keeping blocks of the file consecutive on the disk would have advantages in some storage types such as hard disk, meaning that if I have like this is my disk, okay, and if I store my blocks next to each other, then it's really nice, because as I read them, if I'm reading them sequentially, then I can have a really nice transfer rate, okay. But is it always doable? This is something that's maybe preferable for me, but it has it may also have some uh, down like disadvantages. So in terms of like files, we will discuss four different block allocation methods, and these are basically called contiguous allocation, linked list allocation, file allocation table, and index allocation. So now let's discuss what these things are. Now let's have a look at how blocks are allocated for files in the contiguous allocation scheme. In this case, the file data is stored in contiguous blocks on the disk. For example, here we have a disk and the block numbers runs from 0 to F. We have, and when we have a file X, this X it spans 7 blocks. So what we do is we find a contiguous region of 7 blocks and then use these 7 blocks to store the file X's data. And then comes a request to create a file Y, which needs 4 blocks. So we look for 4 contiguous blocks and allocate them to this one. And then file Z, it requires 2 blocks. Here is a 2 contiguous blocks, and then file Q takes the remaining 3. Okay. Now, this kind of allocation is harder to manage, and it creates external fragmentation. And what we mean by this is allocating contiguous regions becomes problematic, and it has a problem, for example, for file growth. Meaning if I have for file X, and if I need one more data, that means that with this one, if I need one more data block, then what am I going to do, right? In this case, there is no way that I can plug this back here, because it has to be in a contiguous region, because there is a file here. And even if, say, this file Q is deleted, and then I have these empty spaces in these ones, still it will not be easy. The only way that I can do it is I can move all these files Y and Z to the end and then allocate some space and then do it here. Okay, and this is a very problematic size. And more, we will have what we call external fragmentation, and here's like how it happens. For example, in this case, let's say that file Y is deleted, so all these 4 blocks are empty, and then file Q is also deleted, so we have another 3 blocks are empty. So all these we now have 7 empty blocks. Now imagine that I have a new file, say R, and then this requires, for example, 5 blocks. Okay, so I need to find a region, a contiguous region of 5 blocks, which does not exist here, despite the fact that my free space this time is 7 blocks. Okay, but I do not have space. So this is called external fragmentation. We have seen this in the case of memory discussion, version memory discussion, but we will also redefine it as we go. Now, this external fragmentation, as we have seen, things like body system or free lists of various sizes are used, but this is very problematic for disks, because like moving any kind of, for example, in this case the only option that I have is I may have tried to move file Z from this location to some other location and then create that, but that will take a long time. And more, in a hard disk like scenario, the size is not known in advance, meaning that when you create a file, you really you may not know what the size of the file is, whether it typically grows in time as more data comes. Okay, and this is very problematic. Yet this is this idea of having a fixed size for every files is very easy to implement, and it has an advantage of fast sequential access, because when we look at this allocation, the data is stored in contiguous regions, meaning that the access will be fast. Okay, and this gives an idea. For example, this type of allocation is being used on DVDs and CDs. Okay, and it makes sense because when you typically these mediums are used for example, storing videos or other media, where we have the size, it doesn't usually grow over time. It's written once and then read many times, and more, when you try to read them, you really want fast sequential access because you're watching a movie. Now, another allocation scheme for allocating blocks to files is called a linked list allocation. In this case, we create a link, and this link information is used part of the data block. So this is one block on the disk. So we use most of the block to store the data. Okay, but at the end of it, if you need more space, then we save the, like in this case, okay, number of bytes at the end to use as a pointer to the next block, disk block, where the next second data block resides. Okay, so for example, imagine that this is my file A, and with file A, we say that this is block say 5. Okay, so we keep this link that file A starts at 5. Okay, and it requires 4 data blocks to store the data. Now we store some amount of it, and then here, then let's say that we can store the second one as block 7, and then maybe block 2, and then block 4. Okay, so at the end of this, we write the disk block, which effectively points to our next data, and then here you have 7, which now blocks to the third one, and then here you have sorry, this one's making a mistake. So here I write 7, that's the, and then here I write 2, and here I write 4, and then this is the null. Okay, so for example, if the disk block takes 4 bytes, then when we have a 4 kilobyte block, then we will be using 4092 bytes for data, and then use the remaining 4 bytes as the pointer. Okay, now this is nice because now the files can, in this case, grow. They can grow easy. We can do them shrink. It's fine, and it can it can grow as much as the disk. It's fine, but so it's also okay for sequential access. Okay, because at the end of each block, then you have the pointer to read for the next one. But when it comes to random access, okay, for index files, then we have a problem. Okay, this is where we have a problem. That's because imagine I want to read some data from here. Okay, now how do I get to here? Now, in order to find out which data block that I'm in, I have to start from the first one. Okay, I have to read the first block. This is a disk access. Then you get the pointer for the next one. Then you read the next block. You get the pointer, and then you need the third one. You get the pointer, and finally you read your last block, this block, and then access this data. Okay, so this means that traversing a link chain requires a full read-or-write blocks, and this is very bad in terms of access, because in order to access on this data, I need to access basically 3 additional disk accesses just to traverse the link. And you may think that, well, we do caching, but caching does not help, since these data blocks are, say, of size of 4 kilobyte. So that's really large. So you cannot, any kind of caching will not be useful. Now let's have a look at our third file to block matching scheme, which is called File Allocation Table, or FAT for short. Yes, this is the FAT that you will learn. It's the file system, right? Now you realize that when we were doing this linked list idea, okay, which was nice, but we had this link. This would point to the next one, and here's this next one. This would point to another one, and etc. Correct? And the problem that we had was that, these link parts that we have here, they were part of the data, and it made it very slow. So what if we take these links like this, okay, and we put them into one single, we kind of store this kind of linked list information in a table, okay? So instead of mixing with with the data, so here we have this data, so we just create a table which holds these links, and such that now I can keep this one in the memory and I can traverse much faster. Okay, now that's the main idea behind this file allocation table, or FAT. Okay, and it is essentially a FAT. It's a table of next page pointers. We just put them together, and here we have, you can see that, this, in this case, this is our table. Okay, this is the FAT table, and the table has basically one item per disk block. Okay, as here we have this in this table. This is this is indexed by the disk block numbers. Okay, and this is the table content. And initially, imagine that we have all the pages are free. Okay, so there are no files. So we have this free list. This is like a file which starts at 0. Okay, and it says that, okay, like the next block for this free list is 1, which is this one. So this is 1. Okay, this means it's pointing to this one. And now for this one, it's pointing to 2. That's basically, you can see it in here. This one points to 3. So this effectively traverses the whole table. Okay. Now, in this, in this case, we can imagine this free list, which is a list, or which is, we can imagine this as a virtual file that spans the whole disk. Okay. Now, let's say that we create two files, and we have file A. Okay, and with file A, we point to 0. Okay, so let's see here with file A. Okay, the first data block resides at 0. Okay, so this is the 0th data block. Okay, and then it says that, then, if you remember in the previous case, at the end of the data block we had something that's a pointer which is saying where the next block was. Okay, so in this case, instead of this information is stored in the table, in the FAT table, so it's saying that the next block for file A is stored at 6. Okay, so that means that I have on my disk, I have the 6th block. Okay, so let's call this data A1, and then this one has A2. Okay, so now this goes to we have this pointer to here, and then it points to -1, meaning that that's it. The file A contains only 2 data blocks, and they are stored in disk blocks 0 and 6. Okay, what about file B? So here's our file B, and in this case, here's my file B. Now it says that the first data block that I have is, we can see that it's at block 1, because this is block 1, this is block 0, right? So my B stores in here. And then in here, if I need to re-access the next one, it's saying that it's at block 4. So you can access, you go to disk block 4, and there is my second data block for B. Okay, and then by following this, then it says that, well, the third data block is in block 5. So my B3, that's stored in block 5. Okay, and by following this up, then I end up at -1, meaning that, well, it's a null pointer. So my file B basically contains data blocks 01, 4, and 5. Okay, so this is the idea, and you can imagine that, like, unlike in this particular case, traversing, when I'm doing a random access, I have to read all these data blocks, this one and then this one, and so traversing means that I have to read all these data blocks into my memory. Okay, in the FAT table, this particular data structure, which is called FAT, the file allocation table, this is really small. It's because it only contains these pointers. As a result, if I can keep this in the memory, then accessing, for example, a data like here requires it only to go over that. For example, imagine I want to read some data in B3. Okay, and what do I have to do is you go to here. Now this FAT table, if it's in the memory, you follow the link, you follow another link. Okay, sorry, you follow here, and then you get, there you go, it's 5, and then you go to area, you access the 5th block, and you get your data. So traversing in this case is way easier and faster. Now let's look at an example. So what would be the size of this file allocation table? Well, this is a table, and in this table we have basically these FAT entries. This is essentially the FAT entry contains the disk block numbers. Okay, and how many items do I have? The number of FAT entries, well, it's again it's equals to the number of disk blocks that I have on my disk. Okay, now let's work through this example. Let's say that I have a block size of 4 kilobytes, which is 2 to the power 12. Okay, and then I have this disk of 4 terabytes, and it's 2 to the power 42 bytes. So by dividing them, I can see that my disk has the number of blocks on my disk is essentially 2 to the power 30. Okay. So if I have 2 to the power 30 blocks, that means that my block ID can be represented with 30 bits. Now that is roughly 4 bytes. So if I have a 4-byte representation, then I can store my block IDs. Okay. So this means that the FAT entry that I have here, in which I am storing the block IDs, should at least be 4 bytes. Okay. As such. Now, how many FAT entries do I have? Well, I can see it here. Like, how many blocks do I have? I have 2 to the power 30 blocks. So, and I need to have 1 entry per block. So that means that the number of FAT entries is also 2 to the power 30. And as a result, the FAT size would be 2 to the power 30 entries times 4, which is the size of a single FAT entry, and which is 4 gigabytes. Okay, now this is large. Okay, and this is a large amount, and we'll see basically why FAT is like not so. This shows that keeping this much of big of a table does not makes it suitable to deploy on large disks. Okay, so it's, in any case, let's focus on that it's large, but it keeps this file to data mapping. And one way to reduce the table size is to increase the block size. Okay, to make it smaller. So if instead of setting my block size as 4 kilobyte, what if I make it 4 megabytes? Okay, if I make it 4 megabytes, all of a sudden instead of having 2 to the power 30 entries, then I can have only 2 to the power 20 entries. Okay, and that would reduce it. Of course, if that is the case, then you'll have internal fragmentation, and which means that even a small file would use a 4 megabyte, a whole block on the disk. Okay. Now, what are the typical operations on this? So, how do we find the free page? Well, we have a free list. Okay, which points? We can just use the first page in the free list. So it's basically constant time. It's very fast. How can I mark a page free or allocated? Well, all I have to do is to add or remove it from the chain. It's just an update. Okay. Now you can see that contiguous allocation is difficult. Well, I mean, the list may contain block size, but it's not really well. And it relies on caching, meaning that, it's efficient only when we can store this table in the main memory. Okay, if we can keep this table in the main memory, then it will be very useful. Okay, now with the fat, note that each file is represented as a sublist in this table. Okay, for example, we have file A. Now file A, for example, points to, like, it starts at 0, so here we have some sort of a structure which associates file A with the first disk block of 0. Okay, this is saying that the first data block of file A is in disk block 0. And then what about the second one? Well, then for this we need to go to the fat table, and in the fat table it says that the second data block for file A is in block 1. Okay, there we go. And where is the third? The third one is at 4, and the fourth one is at 8, and that's it. Okay, so when we do a sequential access, we do linked list sequential traversal, but when you saw it's fine. When you try to access to nth block, then it's basically a linear scan of the list n times. It's basically we are going n times, we are traversing these links within this table. So that is very reasonable. And this is basically feasible when we have this fat table in the main memory. Now let's look at last file to block mapping, which is called indexed mapping. Now in this case, what we do is for each file we keep an index of data blocks. Okay, and we will see how this is being done in Unix and Linux, where we keep a tree of block pointers in a structure called inode or index block. Okay, now similar ideas have also been used in NTFS, where basically these block mappings are kept in a database area together with other file attributes. And whenever you want to do a random access for a given file and offset, then you return the data address very quick. And in XFS, RiserFS, for example, uses a v+3 for file and offset to data block mapping. Now, what we will focus on how basically the index mapping is used in the Unix case through the use of inodes. Okay, so in Unix there's a structure called inode or index node. Okay, and in this node it's kind of the identity card for the file, and in this identity card we keep track of, along other things, we keep some attributes of the file, okay, as well as pointers to the data blocks. So we have four types of links to here. Okay, the first ones are like a direct one. For example, the yellow blocks here each refer to the data blocks of the data block of that file. Okay, so for example, the pointer that we have here is saying that if I have a file, okay, and in this file, if like my data blocks are, you know, D0, D1, and D2, and so on. So the D1 that's stored in this block, okay, now it's stored in this part, okay. So if this is block, for example, 56, then I am writing 56, okay. And then the second one, this is the second data block, okay, pointer. Maybe this is, you know, 78. This is where I have D2. And the third one is as such, okay. And obviously this does not scale well, okay. It's fine for the first few blocks, but what if we have more? And then we have these indirect blocks. The indirect block points us to a disk block which contains pointers to data blocks, okay. So let's say that, you know, in this case, this one contains D3, okay. Now the indirect pointer here, it points to a disk block. Now, let's say that this is 12, and we have 12. Now the first item, the first pointer that I have here, then that this is where my D4 is stored, okay. And whatever this index of D4 is stored in here, and the next one then contains D5 here and D6 and so on, okay. And then the next item, the next field in here is called double pointers, double indirect pointers. And in this case, this points to a data block, this block here, which contains pointers to other data blocks, disk blocks. And then we can have the next one here. So in this particular case, for example, I have D1, D2, D3 that are accessible by these direct pointers, and D4, D5, and D6 here is accessible by these indirect pointers. And for the double, then we can say D6, then D7 appears here, okay, and then D8 appears here, okay. And then comes the triple, so you get the idea. Now through this, as you can see that for small files, I can directly access the first few blocks. For larger ones, then I have to access, like it's an indirect access, that I have to first access this indirect disk block, and then only after getting this, then I can access the data files, okay. And if it's even larger, then I'll go double, okay. So this is something that scales very well, and basically is used in Unix and Linux file systems. Okay. Now, I've said that we will be discussing the fragmentation issue. We have already learned this in the case of virtual memory. What we mean by fragmentation, it refers to unused and useless areas on the disk. Okay, and we have two types of fragmentation. The first one is internal fragmentation. So let's say that here's our physical memory, and let's say that we have a block size of 4 kilobytes. Okay, and we have the blue regions here are basically allocated to different files on our disk. Now, imagine, for example, since our allocation is in terms of blocks, any file, well, like less than 4 kilobytes would be using basically 4 kilobyte blocks. Okay, so for example, for this 4 kilobyte block, if you look inside, maybe the file actually used only 1 kilobyte, and then, but nevertheless we have to like allocate this whole block to that, so this we wasted 3 kilobytes. Now this is called internal fragmentation because we have space within the allocated blocks. We have unused space within the allocated blocks. Okay, and if we make our pages larger, then you can imagine that the amount of wasted internal fragmentation would grow. And then there is the external fragmentation, and this This happens, for example, in cases where we have contiguous allocation. For example, in this particular case, we have like a lot of empty slots, empty disk space in here. Okay, so in total we have almost 24 kilobyte free space, but there is no contiguous free area larger than 8 kilobytes. Okay, and as a result, for example, this may like if I want to store any file, then I have to like jump from here. If it's a contiguous allocation, then I will not be able to store it at all. Okay, so one way is like, for example, that this is what we call as external fragmentation, that we have some unused space between the allocated blocks. Okay, and then no useful contiguous area is left on the disk, where the total amount of free area is large. And usually when you do, like if you this is a case where we still kind of defragmented the whole thing, and in this case we have this one large contiguous area, okay, that can be used for that. Now we have been talking about basically blocks, and the block size basically it's affects and is also affected by the storage device's native block size. Okay, each disk, well, whatever you buy, it has a native block size, so that block size says that you cannot do any smaller read or smaller writes or updates and etc. Okay, and this is also being used in like virtual memory page size and so on. But the file systems may choose what we call a cluster of blocks as a unit to support larger disks and file sizes. Okay, this is, for example, especially important, for example, in the case of the fat table. If I want to reduce the size of the table, it means that I have to make larger blocks. But what if what if the block size of my disk is small? Then you can cluster them in these units. Now note that when you have a large cluster size, you will have larger internal fragmentation. For example, if I have a 4 kilobyte block, and then instead of this, if I make this 4 megabyte, okay, then all of a sudden, your internal fragmentation will becomes large, okay, and if I have, on the other hand, if I have small cluster size, then it will be bad for locality. So how do we represent the free space on the disk? Okay, so this is called free block management. And one way to do this is to use bitmaps. And basically, for each block, we use a single bit of information, 0 for free, and 1 for in use if it's part of a file. And as a result, we can have a very compact structure, data structure, to represent the free bits. In this particular case, for example, this 1 indicates that block 0 is in use. Block 1 is free, block 2 is free, block 4 is in use, and so on. So this is a very compact representation, and we can see that we use 1 bit per block. So basically we take the total size of the disk, you divide it by the block size, so this gives you the number of blocks on the disk. Okay, and if you have 1 bit per block, then in order to understand how many bytes it takes, you have to divide it by 8, because 8 bits equals 1 byte. So that gives you a size of the bitmap. So for example, if you have a 4 terabyte disk, which is 2 to the power 42, and we have 4 kiloblocks, that means that we powered 12. So in the end, we will have 2 to the power 30 blocks. Okay, and now this means that the size of the table bitmap, okay, is basically 2 to the 30 bits. in order to convert this, we divide it by 8, so that's basically 2 to the power 27 bytes, okay, which is 128 megabytes. Now, a typical operation on this structure is that to find a free page, and basically you scan this until you find a 0 in this map. It may require a full scan of the bitmap in the worst case if it's full. And marking a page free or allocated, it's a complete, we have to write a complete block. It's read or written, because this is stored on the file. And if you want to have a contiguous allocation, it means that I need to do a full scan of the bitmap in the worst case. So this representation relies on caching, because 128 megabytes is a large space to keep in the memory. So most operations are carried in the main memory and then written afterwards. It is a fixed size, no matter how full or empty the disk is. So the size of the bitmap is the same for a free disk as well as for a full disk. Okay. Now you can note that if you do, since part of this structure, like say that this part, it's brought into the memory, and these remaining parts may be on the disk. So when we do like change the values to here, to 0 to 1, or 1 to 0, etc., and if it's in the memory, so it's like, you know, cached in. And if there's a shutdown, and then as a result, this portion of the bitmap representation will lose its integrity, and as a result, you know, this can cause some problems that we will discuss later. Another way to represent the free block is the free list structure. It's basically we keep the free blocks as a linked list. And if you remember our approach, that where we have this linked list structure, for example, here we had file A, it would point to this one, and then in the last part it would point to the next one, and so on, right? Now we can use the same idea to have the free list. In this case, the free list contains data. Okay, so this is the first block of the free list, but as data, this first page contains the disk block numbers of free blocks. Okay, and we use this when it's full, and the last one would point to the next free page block. Okay, so this is the same idea. This is the linked list representation, except that in each of these pages, okay, the entries that we have are entries, okay, they are essentially the disk block IDs of free pages, free blocks. Okay, and the last one that we have here is a pointer to the next one, as I have pointed out here. Okay, now this representation, as I said, like the data part contains as such, and we can just traverse the link chain as such. Okay, now this representation is nice because the free list representation, it's when the disk is empty. Okay, this means that the free list is large. Okay, it takes many blocks on the disk. When the disk gets full, then free list becomes shrinks. Okay, so is small. Okay, you can do this like, if this is my free list, and if I have say 5 pages, 5 blocks left as empty, then everything would fit into this block, and then all these things are not used. So this is a very nice property of this free list, that you can again do the computation of how long it would take, and then you can, for example, we can do this computation and then realize that, like, initially when you first formatted it, it occupies many blocks on the disk. Okay, but as the disk gets full, more and more files, then the free list shrinks and shrinks, so it disappears. So it actually is using the space that is unused by other files. Now, when we talk about a file, we looked into how we can represent its data, okay, and how we can allocate blocks for that. And now a file also contains other things, what we call as attributes. Okay, what are these attributes? And first and foremost, it's name. Okay, this is the only information that's kept in human readable form, and the file, or the name of a file, is separate from your data, right? And so you have to store this information in another place. Another one is like the file attributes is the identifier. This is a unique tag. In this case, for example, in Turkey you have this TC kimlik no, or in US you have the social security number. It's a unique number that identifies the file within the file system, and each file has such a name. And then we have type, which is like the type of the file. Is it an executable? Is it a text file, etc. So this is needed for systems that support different types. And location, a pointer to the file location on the device, meaning that where is it? Where is this file located on the disk? Its size, current file size, its credentials, who owns the file, okay, and the user, the group, etc. Its permissions, what type of accesses are granted for different groups, timestamps, last access, modification, attribute change times of the files, etc. Now, note that the file attributes are kept separately from its data, again, as I have shown in here. Now, the file type or extension, well, this is, as we know, that it provides information about what can be done with that file to the operating system. For example, in Windows, it uses 3-letter code following a dot as such. When you have .exe, it's an executable. If it's .c, it's a C source file. Okay. In Unix-like systems, it doesn't rely on extension, but look at the first group of bytes to determine the file type. For example, it's the ELF binary or a script. And so you can look at this man file or man magic to basically find out how Unix systems does that. And in Mac OS, then text application is used for all files, and the creator application is stored as an attribute so that it can be opened as such. Now, where do we keep these file attributes? Well, different file systems store them in different places. In the FAT, it keeps in the directory structure, as we will show in detail. And so the directory entry also contains the file's attributes along with its entry point, which is the disk block number of the first block of that file. In Unix and Linux systems, the inode structure, it's essentially a block containing all the attributes of the file, stores that. And this basically, we have one inode per file, and it also contains, as we have discussed, pointers for the data block. In the case of NTFS, Master file table database contains the file attribute mapping. Apart from the files, we also have directories that are used to group files in a file system. Okay, it is essentially provides a means of organizing files, typically in a tree structure. And essentially, a directory is just a special files that links the file names. And note that file names are things that are in human readable. So this is human readable text. Okay, to their file system internal identifiers. For example, in this case, in our case, the file name can be your name. Okay, an identifier can be your, TJK McDowell, right? And arbitrary changes on the directory files are not allowed, because access to these directory files, it's a structure that is basically important, and the integrity of this directory trees has to be preserved. So accessing these files, even if they are yours, requires special access. So there is a set of system calls for accessing and updating directories only, and such as make dir, change dir, remove dir, read dir, etc., etc. Okay. So the operations that are performed on a directory are, you may be searching for a file. So it means that given a name or a pattern of names, then you want to find all the files that use it. Okay, you can create a file, delete a file, list a directory, rename a file, or traverse the file system. And don't worry, you've been using this for a long time, but in your third assignment, you will be basically implementing such functions that operate on this small simulated disk. So when we do them, the directory requirements is that efficiency is very important. For example, when you type in the name of an executable, how do you locate that file quickly? Okay, that's very important. You want to support naming that's convenient to users. For example, you can have two users may have the same name, like hello world, for different files. Like you may have your own hello world, so that hello world you should map to a different file, to your friend's file who shares the same name. Okay, or same file can have several different names. And there's some sort of grouping, that's logical grouping files by properties, like all programs, all games, and so on. So the directory organization is important. In the early days, the mainframes used a flat structure, okay, but in their file systems, each user would have a cylinder. This is a separate kind of like a container for files. That means that you have your own kind of disk portion, and so that whatever your names is not mixed up with somebody else's. Okay. In modern systems that you use an array tree in directories as intermediate nodes and other file types as on the leaves. So here we have this. Here we have the root, temporary, another directory, and in the end you end up with all the leaves of this tree correspond to actual files. Okay. Now, with such, I want to discuss links, and what we mean by links is two or more paths. Okay, here we have paths accessing the same node. Okay, so you can see in this structure, for example, I have a single file, and this file appears in two different directories, and they can be accessed through two different paths. It's the same file, but being accessed through two different ways. So this transforms the tree into a directed acyclic graph as shown. Now this provides a more natural categorization. For example, imagine that I'm storing my photos and I want to store them based on its place on the years. Okay, so as a result, a picture that I have taken in CN 334, I want the same picture to be appear in my places method or years 2020. Okay, now of course you can duplicate this, but when you duplicate it, it means that now you have the duplication problem, that if I edit this one, then this one will remain separate, so I really don't want that. Okay, now as such, the downside of this is that you have to be very careful during files removal. So if I get into this directory and if I remove this file, what would happen? So if it disappears, then I'll have a problem here. So you need to make sure that the file's content are deleted only if it disappears from all the directories that it is shown inside. And more, you have to be careful during backups, okay? Because otherwise, a simple backup would just go a breadth first, basically a traversal all this, and as a result, if you go as such, then you may be duplicating this file in the backup, and that will be something that's unintentional and not desirable. Now, the links that we have, there are two kinds. One is hard links, and in hard links, it's completely transparent, and the directory entry points to the same file position. Okay, and there's no distinction between the original and the link. And in Unix, you have this link command that basically creates a link in here. So here's this example. Like I have this file in particular, and what I do is, now this file was initially under this basically this cnc directory here, okay, and I also want this to be appear in my tmp directory. So you do this, and now under tmp, okay, homework2.c would point to the homework.c on this one. Okay, so and they are the same. Okay, there's the completely transparent. And then there's the soft links or shortcuts in Windows. These are called also symbolic links. Now what this does is it's a special file implemented as a redirection. So in this particular case, if I want to do the very same thing as such, then you can do this in Linux as such with this -h, meaning that it's a linked list. Sorry, it's a soft link. And what you have here is essentially a kind of like a special file which includes the path to the actual file that appears in here. Okay, so in this sense, now this one is another file, and it points to here. Now, in this case, there is a difference that, like say you can access the same file from this directory or from this directory, but in this directory, if you remove this, nothing happens to the original file. Whereas in this directory, if I remove this file, then this file is gone, and this shortcut will remain as a dangling pointer. So to wrap things up, hard links, they're more efficient. The downside is they cannot span multiple file systems. So you can have hard links within a file system, and you cannot link directories. The soft links, they can span multiple file systems because you just have type in the path for that file. It can link directories, but it may dangle, meaning that the link may exist without the target, or when relative, it can be moved within the original file. And directory linking may cause cycles, okay, meaning that, and this is really bad, it causes no problems for the operating system, but the programs of accessing the file system recursively may end up in infinite loops. Okay, and of course the operating system usually deals with this, break these cycles by limiting the total number of link expansions in a path. So this ends up our discussion on the file system concepts.